So in linear interpolation, we're going to come up with an estimate that takes into account the maximum likelihood estimates at the trigram, bigram, and unigram levels. And this new estimate is actually going to be a weighted average of these three maximum likelihood estimates. We have three additional parameters, lambda 1, lambda 2, and lambda 3, and these dictate the relative weights of the three maximum likelihood estimates. And we have some constraints on these lambda values. They have to sum to 1, and they have to be greater than or equal to 0. So for example, we might have lambda 1 equals lambda 2 equals lambda 3 equals a third, which basically means we give 1/3 weight to each of these maximum likelihood estimates. So let's go through a specific example, a specific parameter. Say we want to estimate the parameter corresponding to the probability of the word laughs, given that the previous two words are the and dog. Under this definition, and assuming that our lambda values are all equal to a third, we would have 1/3 times the maximum likelihood estimate of laughs given the and dog, and then 1/3 times the maximum likelihood estimate of laughs given just the word dog, and then finally a third times the maximum likelihood estimate of just laughs without any contextual sensitivity. So the motivation for this step is that in practice we end up with a new estimator which incorporates information from all three maximum likelihood estimates, and thus in some sense incorporates the strengths of all these three estimates. So we now have a new estimator which is sensitive to the previous two words in the context, but the estimator is also robust in that it does incorporate information from these more robust estimates at the bigram and the unigram level. So shortly we'll see how we can actually estimate these lambda parameters, again using some data. But first I want to show you an important point, which is that this parameter estimate Q is in fact a valid estimate. So it's important to verify that our estimate correctly defines a distribution. And by this I mean the following. Define V primed to be the vocabulary together with the stop symbol. And now for any UV bigram we're conditioning on, we want to make sure that if we sum over all words W in V primed, we have something that sums to 1. And that's fairly simple to show. I'm just going to go over that in this slide. So here are the steps in proving this property. So what I've done here is substituted for Q the expression I just showed you on the previous slide. So this is the interpolated estimate. So I have lambda 1, lambda 2, lambda 3, these three parameters dictating the relative weight of the three estimates, and I have my three maximum likelihood estimates, the trigram, bigram, unigram estimate. So the first thing to notice is that these lambda parameters do not vary as W varies. So they can be brought outside the respective sums. And so this expression simplifies slightly. I have lambda 1 times sum of W of here, plus lambda 2, I have a sum of W here, plus lambda 3 times sum of W of the unigram estimate. Next, we can notice it's simple enough to show that these sums are all equal to 1. That's because the maximum likelihood estimates themselves correctly define a distribution. Or equivalently, you can go back to the definitions in terms of counts and convince yourself of this property. And so we end up with simply lambda 1, lambda 2, lambda 3, the sum of these three terms. And by definition, remember this was a constraint on the lambdas, these three terms sum to 1. It can also be shown, this is the other property we need for this to correctly define distribution, that for any UV bigram for any w in the set v primed, this value is greater than or equal to 0, and that's trivial to show in this case. So the final question we need to answer is, how do we actually estimate these lambda values? So this is generally done as follows. So firstly, we'll take part of our training set, and we will take some of our sentences, and we will take some of the sentences in our training set and hold these out as what is called validation data. So you can visualize this as follows. Imagine we have our training data. It consists of many millions of sentences. We might take some portion, some relatively small portion, and roughly speaking, say 5% or 1% of our data, and use this as what we call validation data. So the counts used in the maximum likelihood estimates will be taken from the main portion of the training data. But in addition, for any trigram W1, W2, W3, I'll define C primed to be the number of times that trigram is seen in this validation portion of the training data. So we then proceed as follows. We're going to define a function L, which is a function of our three parameters, which basically measures how well our model fits the validation data. So L is defined as follows. We have a sum over all trigrams, W1, W2, W3, and then here I have C primed. So this is going to be the number of times this particular trigram is seen in the validation data. Many of these counts, of course, are going to be 0. And then over here I have log of Q of W3 given W1, W2. So this is my parameter estimate for this particular Q. And Q is defined through the lambdas. So in fact, hidden in here is an expression which depends on the lambdas. And it's defined as before as the weighted average of these three maximum likelihood estimates. So as these three lambda parameters vary, these Q values will vary, and because of that, the function, the value for L will vary. And so we'll set up an optimization problem where we attempt to maximize L under our constraints that these lambdas are positive and that they also sum to 1. So again, you can interpret L as a measure of how well the particular values for lambda 1, lambda 2, lambda 3 fit the validation data. And in fact, it's a fairly easy exercise to show that if you maximize this function with respect to the lambdas, you also minimize the perplexity of the model on the validation data. So we're actually trying to pick the lambdas that minimize the complexity of our language model and hence fit the validation data as well as possible. Now, I'm not going to go into any details of how this maximization is performed in practice, but it is in fact a fairly simple operation to solve this problem. I want to talk about one last issue which is important in practice. And this is intended as a sketch, but you'll hopefully get the idea. And this is that in practice it's actually very important to allow these lambdas to vary a little bit, in particular to allow them to vary depending on the different counts used in our estimate. And here is how this is done in practice. So say we're conditioning on a particular bigram, wi minus 2, wi minus 1. We're actually going to partition different bigrams depending on their count. So in this definition, I have a partition into 4 different subsets. So this function pi takes a bigram as input and returns 1 if the bigram count is 0, returns 2 if the count is between 1 and 2, returns 3 if the count's between 3 and 5, and returns 4 otherwise. So this partition is generally chosen by hand, but this is probably a fairly typical of the kind of definition you might see. Now, once we've defined this partition, we give a slightly refined version of a linear interpolation, where these lambdas vary depending on the value for pi. So I now have parameters lambda 1, sub 1, lambda 1, sub 2, lambda 1, sub 3. And these three parameters are used if the count of the bigram is equal to 0, where I have parameters lambda 2, 1, lambda 2, 2, lambda 2, 3. I use these three parameters if the count is between 1 and 2, and so on and so on. So notice that these lambdas now vary depending on which partition the bigram falls into. Now, what's the motivation for this step? It basically means that these lambdas can vary depending on the partition which the bigram falls into, and hence they can vary depending on the count of the underlying bigram. And this is actually important in practice. Again, these lambdas can be optimized using validation data in a very similar way to what I showed you on the previous slide. And one crucial aspect of this is that, in particular, if this bigram count is equal to 0, this parameter lambda 1 will actually be equal to 0, because this maximum likelihood estimate will actually not be defined in that particular case.